Hello all of you. So in the last lecture we have been discussing what should be the mathematical form of the Helmholtz free energy density f of phi to define the mixing behavior and to define the phase separation behavior. So today I will take this further and discuss what is known as the binodal and spinodal lines and the critical points. And then finally I will try to argue that I can also find the osmotic pressures and chemical potentials as a function of f of phi, and therefore if I know this function, we pretty much know everything about the equilibrium behavior of a liquid solution. So what we had started with is that I have to look at the function form of f of phi, and if that is more than 0, that is my function looks like that, or it is upper concave. In that case, we will have mixing. On the other hand, if f double prime is less than 0 or the function looks like that, then in that case, we will have a phase separation. And finally, I was saying that we may not have a single minima or a single maxima. We can have a situation like that, and in that case we have to identify the function value in the range of volume fractions under considerations, and using that I can find whether we will have mixing or phase separation behavior. So I want to take that further today, but before I do that, let's first look at the phase separation case, where I also need to evaluate what should be the volume fraction in the phases that form. So let's say first of all we take the case when we had a convex function, and I was saying that I will start with some phi 1 and phi 2 value, and clearly we have figured out that for them to form a homogeneous solution, whatever the free energy density that comes out to be, it happens to be higher than what we got from here, that is x f phi 1 plus 1 minus x f phi 1 x phi 2, and therefore the system is not going to mix. So there clearly this is not a possibility at equilibrium. So they will form two phases coexisting, which will have volume fractions phi A and phi B. Now the question is, what is that phi A and phi B? How will I find that? So if you look at it, as we are going on the two sides of this, the free energy density is decreasing, right? So let's say for example, if the new phase have the volume fraction phi A and phi B, so one of them is slightly less than phi 1 and other one is slightly more than phi 2. Now this is possible because let's say if I start with a solution having volume fractions phi 1 and phi 2 in the two phases, now this may increase at the expense of decrease in phi 2 as solute will go from one phase to the other. So let's say if solute moves in this particular way, then the top phase is getting a higher volume fraction and the bottom phase is getting a lower volume fraction. If the opposite happens, let's say if solute is going in this particular way, then in that case the phi 1 is going to decrease and phi 2 is going to increase, right. So only for the mixing case the final volume fraction has to be between phi 1 and phi 2. For the case of phase separation, the opposite happens. One of them may decrease and the other one can increase, right. And this is what the phase separation is, and therefore I said that the phi A and phi B need not be same as phi 1 and phi 2. Generally, it is not same as phi 1 and phi 2. So, now if I compare these two situations, you can clearly see that the energy in the phi A and phi B case in the picture that I have drawn here is less than the phi 1 and phi 2 case. So, this was my f of phi 1, this is my f of phi 2, this is my f of phi A, this is my f of phi B. Since the Helmholtz free energy density of both these phases have decreased by going from phi 1 to phi A and phi 2 to phi B, we can clearly see, even without doing the full math, that the energy will decrease as I go from this state to this state and simultaneously from this state to that state, right. But the same is true if I go further down there. That means, if for example, I think of a new state phi A prime here and phi B prime here, that will have an even lower energy in comparison to phi A and phi B. This will keep on happening until we reach this equal to 0 and this equal to 1, because there is a single maxima in the curve. So, pretty much one of the volume fractions are going to decrease and the other volume fraction is going to increase until the system is fully phase separated, because once that happens, then phi cannot further decrease or increase, because we have reached the limiting cases of 0 and 1. That means, you will have a pure solute phase in equilibrium with a pure solvent phase, and that is a condition of complete demixing. Very close to that we see in an oil water solution, the system wants to completely demix. So, you will have almost pure oil on top and pure water at bottom, and it is for those cases the function curve should look like this, because it has to be like this, so that the system wants to completely phase separate. So, let us look at the other extreme that we had discussed, where the function looks something like that. And now, in this case, we have two regions in the graph. In one of the regions, the f double prime is less than 0, and in other part the f double prime is higher than 0. And now the question is, where do we lie on this particular curve to decide whether we have a mixing behavior or a phase separation behavior. So, if we have the phase separation, or if the tendency is for the phase separation, then we are lying in this particular part of the curve somewhere over here, or we are lying somewhere over here or the other branch of the curve. So, now if I start from say two concentrations, let us say phi 1 and phi 2, which are lying in the region where f double prime is less than 0, we will have a phase separation there. So, the first question is, what is going to be the concentration of the two coexisting phases? And the answer to that is that will lie along a common tangent that we can draw like this in the graph, that is basically a tangent to the two minima points in the curve. And these points, let me refer them as phi A and phi B, will be the volume fraction of the two coexisting phases. And to find that particular thing, what we can notice is that the slope of the function f prime at phi A should be equal to the slope f prime at phi B, that is f prime phi A is equal to f prime phi B, and we can find the magnitude of this slope by a simple geometry. So, we can note
that we can draw a triangle like this, and the slope is given by basically this divided by that. So, the y axis is f phi b minus f phi a, and the x axis is phi b minus phi a, and therefore, the slope is given as f phi b minus f phi a divided by phi b minus phi a. Now, there is something interesting here. If, for example, I now start from this maxima point on the curve, and let us say if I go towards any of the two minima, let us say for example, if I go in this particular direction towards this minima right here. So, while doing that, the f double prime is going from a negative value to a positive value. So, you can expect that there would be a point on the curve where the f double prime is equal to 0. Let us look at this particular point in more detail.
So, I am starting from the maxima and going towards the minima, and we are going to have a point on the diagram where f double prime is equal to 0, that is some sort of an inflection point. The same is true on the other side as well. We will have some sort of a inflection point somewhere in between these two points. Now, let us say for example, my phi 1 happens to be here and phi 2 happens to be here, right. So, using the construction that I have done earlier, the net phi will be somewhere around here, and clearly for that net phi, the condition for mixing is not being met, because clearly for this value of phi, what we have is f of phi is higher than x f phi 1 plus 1 minus x f phi 1 phi 2. So, even if that is true, at both of these points, the f double prime is actually higher than 0, because we are past the point where f double prime is equal to 0. If the point lied between this regime that I will draw now, so if the points lied in this regime where f double prime is higher than 0, then we can clearly say that the system has a tendency to phase separate. But if, for example, it lied in the remaining part of that, so let us say for example, the points lie somewhere here. So, even though for these points, the green guys here, my f double prime is, sorry, this has to be less than 0, because we are in the convex regime, and for this f double prime is higher than 0. So, if we are in the yellow regime, we can clearly say that we have a phase separation, because not only f double prime is less than 0, but also we are finding that for the phi value that we will get for mixing condition, the condition that we had for mixing will not be satisfied, because f phi happens to be higher than x f phi 1 plus 1 minus x f phi 2, right. If on the other hand, if I lie in this green regime, then it becomes a tricky situation. So, on one hand, if I find the net phi value for these two cases, I will still have this condition being met. So, using this condition, I can say that system has a tendency to phase separate. However, f double prime is higher than 0. That means system has a tendency to mix, right. So, these two regimes of the phase diagram are referred as unstable and stable regions. And what it really means is that, let's say my phi1 and phi2 are in the stable regime, then in that case, even when the equilibrium state is a state which is phase separated, system does not have a tendency to go there. Why? Because f double prime is higher than 0. On the other hand, if I am in the unstable regime, if I pick volume fractions in that regime, I will always have a tendency to go towards phase separated state, right. So, keep in mind that f double prime is telling me the tendency, but f double prime is not telling me whether we will have an energy minima in that state or we are having energy minima in some other state that is phase separated, right. So, if I am in the stable part of this graph, what we are going to have is that we know that the energy minima is still in the regime when we have phase separation, but there is no tendency to get there because f double prime is higher than 0. And this is something with a physical meaning. We can have a state that remains far from the global minima for very long time because f double prime is higher than 0 and there is not a tendency to get there. In other words, we can say if I give small fluctuations, because ultimately to go from a state of a higher energy to a lower energy will require some kick. So, if I give it a lower fluctuation, then those stable regimes will remain as it is, but if I give large fluctuations, then they have to get to the local, to the energy minima state. On the other hand, if I am in the unstable regime, then any fluctuation will drive me to a state of phase separation, right. So, this state is actually referred as a meta-stable state. That means the state remains mixed as long as the fluctuations are small. If the fluctuations are large, then the system will go towards a phase separated state, because anyway that is the state where energy is being minimized. In the unstable regime, even if we give a very small fluctuation, that is enough to drive the system to a state of energy minimum, and that is the state of phase separation, right. So, therefore, we have these two regimes, and beyond that, clearly if I am in, say for example, here and here, then in that case we are very clear that we will have a mixing behavior, right. So, only in the middle part of the phase diagram we need to be concerned about the phase separation behavior, and in that too there is an unstable regime only in which f double prime remains throughout negative. In the remaining regime, when f double prime is higher than 0, we can be in a state that is metastable, that will remain in a state of a higher energy in comparison to the equilibrium energy, that is the state of phase separation, as long as the fluctuations are not large enough. So, this particular point where f double prime is equal to 0 is called spinodal point.
So, this two volume fractions define what is known as the binodal composition or the coexistence composition.
So, we know that we have a binodal that is giving me two values of volume fractions which are for the state of phase separation, but then we need to be between these two spinodals, so as to speak, for any small fluctuation to drive it to a phase separation. If we are not in that regime, then in that case we can be in a metastable state for very long time. So, with this particular idea, I now want to include the effect of temperature. So, since I have been working at a particular temperature value, if I now want to put that plot in temperature versus volume fraction diagram, then for a given temperature value, we had a phi A value and a phi B value, and between these two we had two spinodal points, which I will refer as phi AS and phi BS. Now, I may imagine that as I vary temperature, since the function value f is a function of temperature, so ultimately we started with a function f of phi t. Until so far we have been working at a given value of temperature. But now, if I want to see what temperature variations will do to that, then clearly this f is going to change. So, if I connect those points for different temperature values, what essentially we have is something like that. So, for any given temperature, I can locate the two binodal compositions, let us say phi A prime and phi B prime here, and I can locate two spinodals phi AS prime and phi BS prime, and this is of course changing as the temperature is increased, right. So, even though I have drawn the curve in this particular way, it need not always look like this. It may look as something else. It may be, for example, a curve like that, right. So, but nonetheless, as long as we have a regime where phase separation is happening, we should be able to define the binodal and spinodal. If phase separation is not happening, then binodal and spinodal clearly does not have any meaning. So, now using that logic, since we were unstable between phi AS and phi BS and stable in the remaining part for the temperature under consideration. Now, if I look in the entire temperature space, what we can say is we have a regime in the phase diagram that is unstable and another regime in the phase diagram that is stable, right. So, depending on where we lie, so if we are in the orange regime, then we are in the unstable part of the phase diagram, and if we are in the green regime, then we are in the metastable part of the phase diagram, right. These curves have a name. So, this one is called a binodal curve. It connects all the binodal compositions. This is referred as an spinodal curve, and now you may notice that as this temperature increases, we have at the peak of this a condition where both binodals and spinodal curve match, and that particular point is referred as the critical point. So, when temperature becomes at the critical point Tc, then we have first of all a single volume fraction, and secondly at that single volume fraction value the binodal and spinodals both are matching. In other words, the regime of the spinodal regime between spinodal compositions decreases as we increase temperature, or the unstable regime decreases as we increase temperature, but stable regime also decreases as we increase temperature, and at the critical point both these curves match. The binodal and spinodal merge at the critical point, and this is actually a definition of the critical point, right? And the reason why it is important is because if I am working for temperature less than Tc, then only we can see two phases forming, right, provided that other conditions are being met. Let us say if we are in the proper regime in the diagram, then two phases may form. On the other hand, if temperature is higher than Tc, we will not see that happening, right. So, we will have always a single phase, because anything outside this orange and green regimes here are where we have a single phase. Let us say if I look at a point here, here, here or somewhere else, we are going to have a single phase in those points, right. So, for all these temperature values and volume fraction values, we are going to have a single phase. So, beyond the critical point, we are going to have a single phase regime, and below the critical point, we may have a two phase regime, right. So, just to think of an example of that, let us say if I look at water below the critical point, right. So, let us say if I am looking at water below the critical point, then if I start with liquid water and if I start heating it, I go to a vapor state, right. At the boiling point of water, we have both liquid and vapor phases coexisting, and that is what is referred as the binodal composition for the liquid water and the vapor. On the other hand, beyond the critical point, we will not have such a point. We will never have a condition where the liquid water and vapor will coexist. The other word to think about it is that we will go continuously from a liquid phase to a vapor phase, and what we have is what is referred as a second order phase transition, as we have earlier discussed when we were doing the phase diagram of water. So, in second order phase transition, we will not have a jump in properties, and the reason actually for that is because we do not have a coexistence, right. So, once we have a coexistence, you may imagine that you will have a liquid water and the vapor, and their compositions of the liquid and vapor will vary, the amounts will vary for a pure component, and this is what is giving rise to the jump in the properties such as density. If I am beyond the critical point, then no such coexistence happen, and when no such coexistence happen, then in that case we can say that we are in the regime of a second order phase transition, where we remain in a single phase regime and still we are going from a liquid phase to a vapor phase, right. So, in common language we say that we will not be able to differentiate between a liquid and a gas once we are beyond the critical point, and the reason is that we are always in the single phase. We are going from the liquid part of the phase diagram to the gas part, but there is no such point in between where you see both of them coexisting. So, there is pretty much no distinction in the properties when going from a liquid state to a gas state, and this is what is the definition of a critical point. And clearly, the critical point is going to vary depending on the material under consideration. In most cases in thermodynamics, we are dealing with conditions below the critical point, but there are circumstances when we are supercritical, that is beyond the critical point condition. Yeah, so if I want to get the expression of the binodal and spinodal, we already know what it should be. So, binodal curve is given as f prime phi A is equal to f prime phi B is equal to f phi B minus f phi A divided by phi B minus phi A, and the spinodal curve is given as f double prime is equal to 0. The critical point is given as f double prime is equal to 0 and f triple prime is also going to 0. That is the mathematical definition of the critical point, because in some sense it is the maxima of f double prime curve, and that has to be the derivative of that particular curve, and that is why we get a f triple prime there, right. So, what I have been able to establish in this discussion is that we have found this magic function f of phi t, for which if the function looks like this, then it should be mixed. If the function looks like that, then it should be separated. We only need to know this particular function. We haven't yet said how will I derive that function, but we know what that function is. In the next class, I will show you that if I know this function, we can also find the properties that you are more used to hearing, such that osmotic pressure and chemical potential, right. So, typically the driving force of the mixing is characterized in terms of the chemical potential or osmotic pressure, and what I will show you is that both of them are also related to f of phi. So, if I know f of phi, I can find the osmotic pressure and I can find the chemical potential, and therefore, in principle all we need to know is this particular function f to get the entire physics of the mixing and phase separation. So, coming from the statistical mechanics background that we have been doing, this should not be a great news, because we already know that the energy function dictates the behavior. But coming from an undergrad thermodynamics perspective, this may be somewhat big news, because we had too many definitions of different terms like chemical potential, osmotic pressure and all that. And what we will be able to show is all these definitions are actually linked together, and we can characterize the tendency of mixing and phase separation using either of that, not one of that, right. I can use osmotic pressure, I can use chemical potential, or I can use f of phi, whichever is convenient to our problem. But nonetheless, if I know one of them, I can find the other variables that we are interested in. So, with that, I want to conclude here. Thank you.